Good morning, everyone. We are Team Quantize, and our solution is AeroMap3d developed for the problem statement single pass drone video to accurate 3D model generation. The core problem is that traditional drone based 3D reconstruction usually requires multiple passes and extensive image overlap. But in situations such as disaster response, strategic mapping, or infrastructure inspection, we may have only one opportunity to capture the area. Our objective is to use that single UAV video along the GPS and flight metadata and convert it into a geo-referenced and metrically accurate 3D model. Let's see our proposed solution. Our solution is AeroMap3d, an AI-powered pipeline that converts a single pass UAV video into geo-referenced metrically accurate 3D model. First, it supports single pass processing. Meanwhile, we don't require multiple drone flights. Second, we combine AI depth estimation using depth anything V2 with the computer vision based structure from motion using cold map. This allows us to combine learned depth information with geometric camera estimation. Third, we use GPS metadata to transform the reconstructed model from relative coordinates into real-world coordinates and recover metric scales. We also provide confidence information so users can distinguish reliable regions from uncertain regions. Finally, the output can be explored through an interactive 3D viewer for visualization, measurement, and analysis. Let's go to our pipeline. Our technical approach is Coming to our technical approach, the system is built as a combination of AI, computer vision, geospatial processing, and 3D reconstruction. Python is used as primary development language, while WholeMap provides the structure from motion pipeline, and CUDA can be used for GPU acceleration. For AI-based depth estimation, we use PyTorch with depth anything v2. For computer vision, we use WholeMap and shift features to estimate camera movement and scene geometry. For dense reconstruction, depth information is used using 3D processing techniques such as TSDF fusion, with NumPy and SciPy supporting the numerical processing. For geospatial processing, we use GPS coordinates and WGS84/UTM coordinate systems. Finally, Open3D is used for point cloud processing and visualization. Yeah, let's go to the methodology workflow now. The methodology workflows are frame extraction, quality assessment, key frame selection, structure from motion, AI depth estimation, geospatial alignment, then 3D reconstruction. We extract suitable frames from the UAV video instead of processing every frame. At second stage, we remove frames affected by blur, poor exposure, or insufficient visual features. At third, we select informative and spatial diverse frames using quality scores and GPS spacing. And the next step is goal map estimates the camera poses and generates fast 3D geometry. And the fifth step is depth anything V2 estimates depth for selected frames. Then the next space is geospatial alignment, which GPS information aligns the reconstruction with the real world coordinates and provides metric scale. And finally, we use the depth information to generate the dense colored point cloud. These are the 7-step methodology is explicitly described here. And this is our output of AeroMap3d application we have developed. Now let's go to the feasibility and viability. Now coming to feasibility, our solution is practical because it is based on existing and proven technologies rather than requiring an entire newly construction algorithm. Technologies such as cold map, depth anything lead to open 3D and PyTorch provide the core building blocks. Operationally, the system requires only a single drone flight with video and GPS metadata. From an economic perspective, the use of software-based and open source technologies reduces the requirement for expensive specialized hardware. The architecture is also modular, so future capabilities such as semantic 3D mapping, image generation, and change detection and this integration can be added. Our challenges are, however, single pass reconstruction has several challenges. They can be, they are of future poor areas. If a scene has very few visual features, reconstruction becomes difficult. And second one is motion blur. High drone speed, vibration, or low light conditions can reduce depth accuracy. GPS errors. Consumer grade GPS can introduce errors in alignment and scale. Weather and occlusion. Fog, rain, and object blocking the scene can reduce reconstruction quality. Computational demand. AI depth estimation and dense reconstruction requires significantly computational resources. These are the challenges we are facing. How can we overcome? We addresses these challenges through intelligent film selection, image processing, improved georeference, robust depth estimation, and GP acceleration for our state. For example, for poor frames, we can get the quality-based frame selection feature in our model. And for second blur and noise risks, we can use RTK and PTKs and sensor fusion to get to resolve this blur and noise. For depth uncertainty, depth anything V2 plus multi-view consistency may work out. At the high computation, GPU acceleration and batch processing will work out. These mitigation strategies are useful to overcome these challenges. Now let's go to impact and benefits. The major impact of AeroMap3d is that it reduces the dependency on multiple drone flights for 3D mapping. Because we work with a single flight, we can reduce mapping time and operational effort. The system uses standard drone video and GPS data, which makes it more cost effective than workflows that depend heavily on specialized surveying equipment. The georeference and metric scale output makes the model useful not just for visualization but also for measurement and analysis. It can be applied to infrastructure inspection, construction monitoring, urban planning, disaster response, and strategic mapping. Ultimately, AeroMap 3D turns a single opportunity to fly into a usable 3D representation of a physical environment. Yeah. And we have given a research paper in this drive link. You can check how our algorithm works using the provided drive link. Here is the research paper we have created. You can view with this link. And now let's go to our prototype. Yeah, this is our prototype. First, as I have told you, let's choose a video. I will choose a turbine video with some flights. First, let's see the turbine video. You can see that there is a green terrain and a road with bushes and some wind turbines here in this video. It is a drone video. Yeah. After generated the 3D model of this drone video. Here we can see the source frame and its meters, depth, and the segmentations. Here. Thank you. This is a prototype we have done now. Here it has shows how many vertices and how many faces, and it is stored in a output file as terrain.ply. With the model stores in .ply format. Thank you. This is from team Quantize.